Okay, we'll get back to section 4.3. We're talking about how derivatives affect a graph. And we were looking at the concavity test in the last video. So the concavity test is this test here. If f double prime of x is greater than 0 for all x on an interval, then the function is concave up on that interval. If the f double prime of x is less than 0 for all x on the interval, f is concave down on that part of the graph. Okay, concave up means that all the tangent lines are below the graph. Concave down means that all the tangent lines are above the graph. A point where you switch concavity is called an inflection point. All right, so we've looked at one example here. And so here's another problem that we'll take a look at. We want to find the intervals of concavity and the inflection points for the function f of x equal x squared plus x plus 1 all over x squared. Okay, so I'll need to find f double prime of x. And when I differentiate, I got a couple of options here. I could think of this as a quotient rule. That'd be fine, although maybe a better way would be to split this single fraction and then I can use the power rule on each one of these terms. So if I split this into 3 fractions and then simplify individually, I'm going to have f of x equaling 1 plus 1 over x plus 1 over x squared. Okay, that'd be the same as 1 plus x to the negative 1 plus x to the negative 2. That way I can use the power rule. Derivative of a constant is always 0. When I differentiate x to the negative 1, bring down the power, reduce the power by 1, you're going to have negative x to the negative second, or that would be negative 1 over x squared in fractional form, plus the derivative of x to the negative second, using the power rule, that would be minus 2x to the negative third, okay, or minus 2 over x cubed. When you simplify this to a single fraction, it's going to be negative x cubed minus 2x squared all over x to the 5th. Okay, but you can factor out an x squared out of those two terms and cancel it with part of the x to the 5th in the denominator, and that would leave you with negative x minus 2 all over x cubed. Now, of course, something that I'd like you to observe here is that when you have a quotient, you don't always have, it doesn't automatically mean quotient rule. Okay, like I could still use the quotient rule and I'd get the same result here. It's just, it's probably quicker to use the power rule instead. Okay, so consider that, when you're taking derivatives. Is that method the most efficient method? I need to find f double prime, so I would say, why don't we go ahead and apply the power rule again. We'll use this form. Negative x to the negative second minus 2x to the negative third. Let's apply the power rule on these two terms. Of course, I could use a quotient rule, but, why don't we try to avoid that? So the derivative of negative x to the negative second would be 2x to the negative third, or 2 over x cubed, minus the derivative of 2x to the negative third, that would be a plus 6x to the negative fourth, using the power rule, or plus 6 over x to the fourth. Okay, and when I combine this to a single fraction, cross multiply, you're going to have 2x to the fourth plus 6x cubed all over x to the 7th. X cubed would be in common to those two terms. You can factor that out and cancel it with part of the 7 x's that would be in the denominator. After you've canceled, you're going to have 2x plus 6 all over x to the 4th then, which would be in simplified form. Okay, now we want to set that equal to 0. And if you multiply both sides by x to the 4th, subtract 6 and divide by 2, you get x equal negative 3. Okay, now when I make my table here, of course, negative 3 is going to go on the chart, but I also need to consider any values for which f double prime of x does not exist. Well, There's a problem with division by 0 here, so x can't be 0. Now, x can't be 0 in the original function, though, right? Since I know I can't divide by 0. So 0 is going to produce a vertical asymptote at x equals 0. And now remember, whenever we make the table, we want our key numbers on the number line along with any numbers that are going to produce vertical asymptotes on the graph. Okay, now I mentioned in the last video, this number here, when you set f double prime of x equal to 0 and solve, is not a critical number. Okay, it behaves like a critical number. You know, this is a key number on the picture that may produce an inflection point, but I wouldn't call that a critical value. Okay, so I'm going to put these two values on the number line and create my chart here and say interval, number chosen, value of f double prime, and then the conclusion. The intervals are these three intervals splitting up the real number line, and now I'm ready to use my test values. Okay, select a number inside of each one of these groups, plug it into f double prime, and see if the result is positive or negative. So in the first group, I need a number less than negative 3. If we use x equal negative 4 and we plug that into f double prime, then we're going to have, let's see, 2 times negative 4 is negative 8, plus 6 is negative 2. Divided by negative 4 to the fourth would be 256. Okay, negative 2 divided by 256, when you reduce that would give you negative 1 over 128. That's a negative. And so because f double prime ended up being a negative, I know I'm concave down on that part of the graph. By the way, make sure that your conclusion is correct here. Okay, I'll have students get these tests mixed up. Okay, and they'll say, well, we got a negative, so we're decreasing. No. The increasing decreasing test is for f prime, right? You're not doing anything with f double prime for increasing decreasing. Okay, so of course make sure that the correct conclusion is there, and you're not getting mixed up with these tests here. How about the middle interval? I need a number between negative 3 and 0. So if we let x be negative 1 and we plug that in, here's negative 2 plus 6 is 4. I'm dividing by 1. I get 4. I'm concave down on that part of the graph. And a number bigger than 0, if we let x be 1, plug that into f double prime. 2 plus 6 is 8. Okay, and we're concave up still. So the intervals of concavity, we're concave up on the interval negative 3 to 0 and also 0 to infinity. We are concave down then on the interval negative infinity to negative 3. Okay, and of course I can see that from the table here already. I'm just kind of restating the results. Now, we're switching from concave down to concave up at x equal negative 3. So, therefore, there's going to be an inflection point at x equal negative 3. And when x is negative 3 and you plug that into the function, negative 3 squared is 9, minus 3 is 6, plus 1 is 7, divided by negative 3 squared is 9. 7 over 9 would be the y value. Okay, and so I'd want to circle that result there. They wanted us to find the intervals of concavity and the inflection points, and we've done that. Okay. Now, if I were to sketch a graph using this information, of course, I got a lot of key information here that I've been able to get. So I've set up a graph. The scaling isn't the same on the two axes. That's fine for what we're doing. All right, now, of course, I can use what I already know from algebra. The fact that we're throwing away 0 as a result of the domain means that x equals 0 would be a vertical asymptote on this graph. Okay, so I'd want a dotted line there right on the y-axis. The degree of the top is the same as the degree of the bottom. These are both degree 2 polynomials. And so I'm going to have a horizontal asymptote at y equal 1. If I compare the leading coefficients there, y is 1. So I've drawn that. And let's see. Okay, so we have an inflection point at negative 3/7/9. And so that's where I'm going to switch from concave down to concave up. Well, concave down means that I'm drawing a curve where all the tangent lines are going to be above the curve. Concave up means that all the tangent lines are below the curve. So I'll switch concavity there at that point. Now I've got an asymptote here. course, the curve has to approach the asymptote. Okay, but you're concave down if you're to the left of -3. Now, the fact that we're concave up means that we're going to produce a local min somewhere between -3 and 0. The first derivative test would help me see where there's a min. So if I were to set f prime of x equal to 0 and solve, multiply both sides by x cubed, add 2 and divide by -1, x would be -2. Okay, if you plug -2 into the function here, you should be getting 3/4 as the output. Okay, so that point there, -2 3/4 would be a local min on the graph. This graph would also cross the horizontal asymptote. I know that because I'm concave down from -3 to 0. I don't switch concavity again. Okay, so it's not like the curve is going to head downward here. I've got a vertical asymptote, but we will cross the horizontal asymptote though too. We're also concave up to the right of the vertical asymptote. Maybe to help me get a more accurate picture here, I can plot an additional point. Like if x is 3, and I plug that into the function, 3 squared is 9, plus 3 is 12, plus 1 is 13, divided by 9. Okay, so here's the point 3. 13/9 would be a little bit bigger than 1. Okay, and of course the curve has to work with these two boundaries here. So I think the curve is going to be heading down the vertical asymptote. It'll be on the right side of it, pulling away from that slightly, and it'll be approaching the horizontal asymptote from above it. And of course I'm concave up on that part of the graph, right? If I draw a tangent line anywhere on that part of the graph, that's from 0 to infinity, the tangent line is going to be below the curve. We're concave up on that part of the graph.